How's it going, everyone? Vlad here, and welcome back to the channel. As you can see by the label of this whiteboard, as probably the title of the video, today we're going to be talking about the manufacturing industrial automation levels. And basically, I'm going to be walking you step by step from what I've seen in my experience when it comes to the lowest levels of automation, where you simply have a start and a stop push button to start a motor, a pump, or another field device, to the very advanced manufacturing processes where you have entire switches and distributed SCADA systems and different VLANs and PLCs. So ultimately, the goal here is not to judge the manufacturers, but I've seen and I have been in many conversations where it seems that a manufacturer that has been operating at a certain level for many years or many decades simply does not understand maybe some of the challenges and the opportunities when it comes to automation. And ultimately, I don't necessarily blame them, because it's also different factors. It becomes a question of culture, it becomes a question of sales of their specific product. So a lot goes into these different layers, but today we're going to talk about the technology side. And of course, if you have any questions, if you're working in manufacturing, if you're a leader in manufacturing, if you have any questions based on any of these topics, make sure to leave them in the comments. Make sure to stick to the end of this video. There's going to be a lot of different layers to discuss. I'm going to be giving you tips. I'm going to be giving you tricks on how to improve your manufacturing process, and ultimately what challenges should resonate with you depending on every level. So we're going to talk about the most basic level of automation. And usually I've seen this a lot in food and beverage facilities, in farms, for example. So what I'm going to draw here is an auger, right? So if you have an auger that goes from a silo, so I'm going to again make a couple of drawings that are going to be not to the life-size replica. If you have an auger that goes from a silo, where for example here you have some kind of a manual valve where the grain drops and then it's basically going up to this conveyor. And here, once again, I'm going to make this very crude drawing of a truck, right? So if you have something simple as a truck that's going to simply take the grain and then drive off to a different facility, all the automation you truly need is here. For example, you have a motor that's going to be connected either to a VFD, but really just to a few push buttons that allow you to enable either the VFD or the contactor so that this auger could run. And again, this could be a different conveyor. I'm just going to create this very crude drawing where the grain goes into this truck and then the truck can then drive off. Do you need a PLC in this case? The answer in almost all scenarios would tell you it depends, right? So if you know that the level of your tank is, for example, 40,000 pounds, but basically if you're going to empty this entire tank into this truck and someone's either monitoring the level or there's a specific switch that's going to allow you to set an alarm where this is going to simply close off the valve, there's really no automation necessary, or very basic. You can use any PLC for this. You're probably not going to do any high-speed applications. You don't really need a network. So really all that's going to be very necessary is to be able to run this auger. So that's going to be two push buttons that go to a contactor or VFD, right? Again, probably directly wired. And this goes three-phase. Again, you have three-phase coming in into the VFD or contactor, and then the three-phase is going to start and run the motor. So this is the absolute basic automation system. There's really no controllers. There's going to be a lot of visual inspections. So what are the disadvantages here? So like I've mentioned, there's a couple of things, right? So number one, you risk overfilling, for example, the tank if someone's not paying close attention. Of course, if someone has some kind of an alarm or a trigger system, then you can start tying in the signal. So again, there's going to be different VFDs that can be set to the point where you have a sensor that's going to stop the specific tank at a certain point in time, but really you don't have a controller, so there's no way to notify somebody if an issue has occurred. And if there is a problem, for example, with the VFD throws a specific error, then it's going to take a while to respond. So unless you have some kind of a notification system that will send you a message on your phone or any kind of device, you're not going to know that the system has failed. So it may take some time before you can repair. But this is the example of the absolute most basic system that you will find in the field. The chances of you even having a electrical panel or an MCC cabinet is going to be relatively slim in this scenario. So I've alluded to this a little bit in the previous example, but as you start scaling your operation, you start having the need for automation. So this is something that happens naturally as you introduce different process or different mechanical components into your system. So for a moment, imagine that you have a more complex design where, for example, you have multiple tanks and you have a system that from whichever direction feeds the raw materials into these tanks, right? So there's going to be three, for example, sections. And I've actually done work on something of this nature. So you have a conveyor belt that can choose into which tank it's going to deposit the raw ingredient. And again, this could be dropped off by a cart, this could be dropped off by bags. There's going to be a lot of different ways that this can be done. But ultimately, you have a valve here at the top that opens up and allows you to fill in the tank. And as the tank fills, you obviously have a little sensor here that's going to measure the level, as well as usually you have a load cell. So the load cell is also going to measure or weigh the tank, so to speak. And so in this case, you have quite a bit more automation needed in order to run the system. And it simply becomes inefficient to run this via just a start and stop push button by using something like a VFD or a contactor. So as you naturally scale your process, you're going to reach this next level of automation where you will need a PLC, an HMI, you're going to need sensors, meaning you need IO, and ultimately, like I've mentioned, there's going to be different components perhaps on the network side that can also tie into your automation stack. But let's take a step back just a little bit. So before we get into networks, right? So now you have a panel where you have a PLC rack, and again, I'm going to draw this a little bit crudely, but you ultimately have a PLC that will be processing various signals, right? So you have ultimately a signal coming from this valve, you have a signal coming from, and when I say from, it's tied to the PLC, but obviously it's an output to open the valve. And so this is going to be different sensors here. Here you have, again, a level sensor. A lot of times that's going to be analog, so that's going to be going into an analog input card on the PLC side. Once again, you have a third sensor. You probably have, like I said, a discharge valve here at the bottom of the tank. You're going to have a load cell. Again, load cell could be analog, so it could come in as an input on the 4 to 20 milliamps. It could be a voltage as well, but it could also be on the network. So let's talk about first of all, the current system, right? So now we've introduced IO. And so at this point, your system becomes a little bit more complex than in the previous example. So now your IO needs to handle either current or voltage, but it also needs to send out signals, either digital or analog. So for example, if you're only opening and closing those valves, so you're not doing any control when it comes to the position of that valve, which is also possible, then you're only going to need digital signals. But if you're going to do position, obviously analog is going to be required. You also need to run both of these conveyors. And remember that running a conveyor is going to be, again, once through a VFD or a contact. And so, of course, as soon as you introduce VFDs, as I mentioned a little bit before, the easiest option, or I would say the most common option in larger facilities, is to do it over Ethernet. So if you have a drive that can talk over Ethernet IP or Profinet or Profibus, I'm just using Ethernet in a general sense because Allen Bradley is a platform that I've been working with for a very long time. So you need a network, but ultimately, let's take again a step back. The easiest way is going to do it via digital inputs, right? So at this point in time, imagine that I don't need to control the speed. I can simply put the parameters in, and so my VFD is going to run at a constant speed. There's other variations as well. So you could set, for example, 3 different speeds, and then you could have 3 digital outputs. And again, we can get into the semantics as to how that's truly connected, but ultimately you have 3 different set points of variation of speed. So ultimately you don't need to readjust the speed every single time. All you're doing is you have 3 set points, and based on the fill level of the tank or maybe the discharge that's going into a different system, you're going to be controlling that VFD again via digital outputs. And so this is the second layer of automation where you basically just have a PLC and you have a couple of IO points and you have a couple of peripherals that will be utilized in the system. The next level of automation that I do want to talk about, and I'm going to keep the same drawing here, is going to be distributed IO over networks, right? So I'm going to skip the step where we talk about device net and control net because a lot of those protocols are being depreciated. but ultimately you are running a network that is distributed to your IO. So what does that actually mean? And I'm just going to make a little bit of space here. So instead of the VFD, I'm going to draw a switch, right? And so a switch, when it is unmanaged, is basically just a box that allows you to pass through your signals. Should you be using a unmanaged switch? Should you be using a managed switch? That is a different debate we'll get into in just a moment. But ultimately, imagine that you have now a card that connects to a port on the switch and then allows the switch to send traffic or to communicate with various devices. So I've already mentioned that some of the load cells, actually a lot of the load cells that I've worked with, are going to be on a network, right? Again, depending on which flavor you buy, depending on the platform, of course it could be different, but ultimately imagine that a load cell is going to be something that holds the tank here. You're going to have a wire, and then you're going to have a card inside of your PLC or electrical panel cabinet, which is going to receive these cables that basically converts the signal based on the weight of your tank into a signal that can be read by your PLC. So imagine that this card, and there's going to be multiples, and I don't have a whole lot of space on this board, but imagine that tank number 2 has some wires going here, tank number 3 has some wires going here. Each one of these cards is going to be on the network connected via the switch that we just drew here, and it's going to pass these signals to your PLC, right? And this is the next layer of automation. What else is possible with a distributed network? Now you have the opportunity to create what's called distributed IO. And so there's going to be, again, different flavors. There's armor blocks, there's going to be on machine, there's going to be different cabinets. So for example, imagine for a moment that you have this specific tank farm, and now you're looking to add a second replica of the same tank farm, maybe at a facility that's going to be right outside of the current one, right? So you've built a second facility on the process side, and now you have a replica of this exact same control system. Does that necessarily mean that you need to purchase all the same PLC peripherals and components? And the short answer to that question is no, right? Because you can, what's called, use a remote IO. So here from the switch, I'm going to draw a cable, right? So this is just a single cable that's going to go into yet another electrical panel. I don't know how well you can see this on the whiteboard, but basically this electrical panel is going to be controlled by this same PLC. And although it has the exact same components, all it's doing is it's acting essentially as a secondary panel that's going to be controlled by the controller and monitored from the exact same system. Now, we've also not talked about HMIs or human machine interfaces, and this is usually where you start needing them, right? So in the previous level of automation, where we talked about non-distributed systems, usually you can have push buttons, and a lot of them are still designed with, let's say, panels. You have an electrical panel that allows you to start the entire system, to stop the entire system, to start and stop maybe specific components. You even have lights for faults. But this is where you start to need what's called an HMI. So again, I'm going to draw this in a very, I want to say, non-realistic way, but you start having a screen instead of push buttons. You have a screen where you can control, where you can read different faults, and this screen also connects to the switch so that it can talk to the HMI. And so ultimately what we've created is a network of different devices that allow you to control a specific process in your facility that all cohesively connects to your field devices, but also allows you to control and monitor what's going on locally, right? So none of this is still being distributed. None of the signals are leaving this specific area, but basically we've created a local network. So let's go back to the question of the switch, right? So a lot of people will argue between the question of managed versus unmanaged switches, right? And so until you connect your plant, or at least until you connect a smaller area to the entire facility, the reasons for which we'll discuss a little bit later, I would argue that there's not a lot of value of having a managed switch, besides the fact that if you have, for example, an operator or somebody opening the electrical cabinet and decides to, for example, plug in their laptop unknowingly and introduces some kind of a vulnerability, you're basically paying a lot of money to make this switch managed. And the reality is the traffic or all of the network should be contained within this system. So let's talk about the next scenario. And this is the scenario where you start having a cohesive production line within a facility. So I'm going to essentially ask you to look at the line that we've talked about before, where you have multiple tanks processing some kind of a grain or maybe product, and look at that as a small system within a larger system. So I'm going to try and draw this as much as I can. So these are going to be your tanks. And basically, this is the system that will interface, right? So you have some kind of a conveying system, maybe a bagger that's going to send the grain over to those tanks, as we discussed. And then maybe this goes to some kind of a processing facility, right? So imagine that this is going to be some kind of a roaster or some kind of a cooking facility, right? So there's going to be different tanks here. And again, I'm going to draw this very crudely. There's going to be conveyors going in from the tanks. Between the tanks, it's going to be cooking, different batching systems. And so you have a system of systems, basically, where, for example, this is going to be the final destination of the batch, and it's going to be two large tanks from which this now gets palletized, for example, or packaged or distributed. So what you run into is, number one, you start needing to have interlocks, right? What is an interlock? This system needs to know when can it send product from the tanks into this batching process or cooking process or processing of whatever nature. This bagger system also needs to know, how do we fill those specific tanks? You start needing to know, for example, SKUs, right? So these bags will come from the outside with different SKUs, and you start needing to track the different SKUs across your systems. And so now it becomes very difficult to manage the paperwork between different departments as those SKUs and as those batches are processed. So what you start having is, for example, you have this electrical cabinet here, you have this electrical cabinet here, one here and one here. You need to start getting them on the same plant network, right? So this is where IT will usually come in, and you will see this on the IT side in the form of Meraki switches or just traditional Cisco switches. It could be HP, it could be Aruba. So the brands don't necessarily matter, but ultimately this is where you start having a plant-wide network. So I'm going to draw this as best as I can. But basically, remember the little switch that we had in the previous example? Each one of those switches is now coming into a port on an IT managed switch. And so we'll get into what the IT side looks like, but basically now that you have connectivity between these systems, you need to start thinking about the network architecture of your facility. And what does that actually mean? What kind of problems can you experience? A lot of times I would see plants where networks are mismanaged, so the IP addresses can be duplicates. The IP addresses or the Ethernet ports can also be connected, for example, like this. And so now you start having a loop, which is going to cause issues. You also have different traffic coming into this IT switch from the corporate side. You can have people with laptops watching videos, for example, which causes traffic spikes, which, for example, if this machine has a safety component, which we haven't necessarily discussed when it comes to automation, but it starts having issues because it requires a very specific latency. But long story short, this is the level of automation where you require to have a robust handle on your networks on the OT side, right? So this is not even talking about maybe SCADA systems yet. This is just talking about connecting the different machines so that we could have interlock connectivity so that each system can communicate to the other one what the status is. This also unlocks the capability of having a managed or a single point of a SCADA system. And so I did an entire video on SCADA systems, but basically imagine that the switch also goes to what's called a server room, right? So a server room, again, this could be a rack, this could be a computer. It doesn't necessarily matter, but ultimately what this allows you to do is run different software in a way that permits not only control of your system, but visualization in a single environment. So remember, like we talked about before, this, for example, bagger area is going to have an HMI. This tank area is going to have an HMI. This process is going to have an HMI. And this final pre-palletizing, pre-packaging system is going to have an HMI. Now, because of the server, what you can do is here you will have a distribute. I'm going to draw a couple of ports, and you will have an operator, as we've discussed in the SCADA video, that can now watch multiple monitors that will tell him what the status of this system is, right? So this is going to be connected, for example, to this screen, to that screen, and to this other screen. And so you will have an overview of all of these areas inside of a single room. And this is what is basically called SCADA. Again, there's going to be a long debate if you could make this on an HMI, and HMIs are powerful enough, of course, to control probably this entire facility or line, depending on which HMI you purchase. But once you have a SCADA, you're really going to have a lot of data and information that you can process in order to improve the state of your manufacturing facility. So what does it usually take to get your networks in order? This is where you start having a managed architecture, right? So this switch usually is not going to be unmanaged. This switch needs to know exactly what sits at every port. And usually, again, when you have a smaller facility, you're going to have a flat network, right? And a flat network basically means that everything has the IP address of, for example, 192.168.1 or .0.xxx. And the reason for that is twofold, right? So number one, if you've worked with Allen Bradley equipment, here I have a Compact Logix, you will know that a lot of the devices, as they fail or as they are commissioned at the very beginning, what you can do is simply set the switches on the hardware that makes it very easy for someone on the maintenance side to replace. So basically, what it takes if it's set to 192.168.1. Whatever, is for someone to just set those dip switches to the value of the device, and they can simply swap it out. So it is, I guess, common to see flat networks in smaller facilities or smaller machines, and we'll talk about segregated networks as well in a moment. But ultimately, the second reason why this is done is for simplicity's sake. So once again, when you have machines that are simply dropped on the plant floor, it's very easy for the machine builder to keep those IP addresses as default, and therefore when they arrive to the plant, they're simply left as is because they are not connected to anything else, and the vendor simply does not know what your factory is going to need in order to create the architecture for multiple machines. So usually the exercise during commissioning, so if you, for example, add a new system, right? So we've talked about adding maybe a second set of tanks here at the very top. The engineers that are commissioning the set of tanks are going to need IP addresses for your PLC, for your HMI, for your VFD if they're on the network, for your load cells, right? So they're going to need a range of IP addresses that they can allocate to those specific devices. And of course, depending on how you do your subnetting or how you set your VLANs, you may not, first of all, have those IP addresses available, but you might also run into traffic bottlenecks. So for example, if this PLC in this specific machine sends the signal that this PLC needs to, for example, stop or shut down the process because there's simply overflow of product, you will also, if it's on the same network, the traffic is going to travel to all of those ports, right? Because again, if it's not shut down, it's going to allow it to talk on the entire subnet. So what you start running into as you add more and more devices is the same issues that we've discussed as you would see with a poor network. So now you're starting to have potential loops. You're starting to have a lot of traffic on the network. As you introduce maybe even vision systems start to send images between different devices or back to the PLC. And so you run into a lot of problems when you have unmanaged traffic. And so I'm going to try and keep this image as best as I can because there's very little space left, but ultimately you can start segmenting your networks, right? And for example, imagine that this is my first storing area, right? So I'm just going to draw a big bubble around the entire facility here, and that's going to be my VLAN, for example, 10. So this is VLAN 10. And I allow all the traffic or all the devices on VLAN 10 to be able to communicate on the same network. And that's going to be great, right? But now this switch needs to route between VLAN 10 and whatever else VLAN is available. So here I'm going to create a second VLAN, and this is going to be the process area, right? So in certain facilities, process areas are fairly intricate, right? So you're going to have different tanks, different devices, different cells, different vision systems. So this is going to be VLAN 20. And last but not least, you're going to have some kind of a packaging area. So we talked about just the storage, but here you have palletizing, you have shipping, you have all sorts of different products. And this is going to be VLAN 30. Each one of those VLANs is going to operate as a separate subnet that allows the traffic, for example, between this PLC and this PLC. It allows the traffic from, for example, this load cell if you need to come back to this PLC for whatever reason. So basically, we've created a segmentation of 3 different VLANs in this example, but we do need the switch to say, hey, sometimes this PLC, or let's say sometimes this PLC, which outputs to this system, needs to talk to the PLC in this VLAN 20, but only between the PLCs, right? We don't want any of the noise that's coming from the other devices, from the vision systems, from the VFDs, from the load cells to go back to, for example, this layer 1 or VLAN 10. And so this is extremely important because as you segment the networks, it also allows you to reuse duplicate IP addresses. And a duplicate IP address is not something you would be doing in any other scenario, but ultimately by segmenting, you can create scenarios where you have devices here in this machine with the same IP addresses as some of the devices in a different machine, but they have the same exact IP address. They're just segmented on different VLANs. So at this point, I do want to take a step back. First of all, if you are still listening, please leave me a note in the comments if you enjoy this type of content. If you have any questions, what kind of level of automation are you dealing with? But ultimately, I want to take a step back and talk a little bit as to why we're going the way the networks are. So in the past, when you had a VFD, we've discussed this a little bit, but a VFD can be started by a start button and a stop push button. So start and stop. And so in this case, as I've mentioned a little bit earlier as well, you get very little diagnostics from your device, right? And the same goes for your sensors, the same goes for your load cells, the same goes for your HMIs and PLC, to be honest with you. So instead of doing a start and a stop, why don't we do current, right? So there's also a way to start and stop your VFD with 4 to 20 milliamp. Again, we can talk about voltage, but ultimately you're starting and stopping and controlling the speed based on this control loop. And so you have a PLC, again, this is the PLC, this is the 4 to 20 output card. It's going to start and stop your device. Once again, if this VFD fails for a variety of reasons, and those could be mechanical, it could be electrical, it could be a failure of the encoder, it could also be a lot of the, for example, voltage problems coming in, this VFD is not going to be able to send a signal over the current line for you to know why it has failed, right? So if I'm looking at a VFD, I'm going to have this little screen, and this is going to say, for example, fault 073, and then I can look in the manual and understand what that issue is. If I connect over Ethernet, right, and I'm going to redraw again, this is going to be a switch. So imagine that my VFD is connected over Ethernet, and this Ethernet cable is connected to my PLC. I can now get this error into my PLC and I can react accordingly, but I can also troubleshoot and display that either on the HMI or the SCADA screen. So I could see, for example, that F73 is torque overload. And this immediately tells me as an electrical engineer that there's an overload, obviously, with the process, but I can go see where this VFD is connected. And a lot of times it's going to be some kind of a process jam. Maybe the materials were incorrect. Maybe the raw ingredients were not to spec. But ultimately, I can see this warning by not having to open the panel and to look at fault 73, then having to look in the manual and then realizing that it's torque overload. I can write that to the operator directly on the HMI screen. So why am I saying all this? So when you're connected over current, or if you're connected over start and stop digital inputs, the chances of you realizing that it's a torque overload and then fixing that issue is going to be much longer, or the response time is going to be much longer than if I'm connected over Ethernet. I can then send this over to an HMI screen with an alarm that will automatically notify the operator, right, within a screen that says overload motor 12, for example. And so I can add a lot of descriptions. And in this case, it's going to take, for example, 10 minutes to fix. And if you were using current, it's going to take 30 minutes to fix. So at that point in time, you need to understand what are those 20 minutes worth to your business, and if it is worth to investing the money to properly automate and ultimately implement a network that makes sense. The same goes about historical information as you start getting into SCADA. If you don't need the historical information, if you don't have a culture that's going to troubleshoot and look at data, you don't necessarily need to invest in some of those tools. But if you see value in shorter response times, in quicker turnarounds from your downtime, then you start having to see and understand where automation ultimately fits. So the last layer of automation is going to involve all the stacks on the ISA conversation. So I'm going to basically draw lines now. I'm not going to draw individual machines, but imagine that each line has different machines all the way from process till the end that is packaged. This is palletizer. This is trucks driving away with the final product at the end of your manufacturing facility. And so you have now multiple processing lines. Of course, they're never going to be the straight. There's going to be always very interesting layouts. If you've been to different facilities, you have different departments, you have different areas, right? So you're going to have storage areas, you're going to have processing areas, all sorts of different things. But ultimately, this is where automation truly comes in for the most advanced facilities. We've talked about PLCs in each individual cell that control the process. Again, the specifics here don't really matter. What's important here is you're going to have an IT room. So I'm going to label this as IT room, where you have servers and you have switches that are networked to all the devices on the plant floor. So you have different cables running from your PLCs that allow you to, number one, segment the networks. It allows you to distribute some of the HMIs, right? We talked about SCADA, so maybe there's some kind of a big SCADA at the start of this line that also runs some kind of data and analytics, but also allows the operators to see what's going on. You have these different areas where you have boards that are called Kanban boards, where you can see the status of your production. Maybe you can see some OEE metrics. And that is where the MES, for example, software comes in. So we talked about servers, but servers can ultimately host a variety of different tools. So MES, or Manufacturing Execution System, there's going to be a separate conversation and video released on that. Will also store a lot of the information coming from the PLCs, the SCADA systems, your HMIs, depending on the architecture, but ultimately allows you to see the operation and how you're doing within your specific organization, within a specific line, within a specific shift, and basically allows you to process a lot of this data. But in order for all of this to make sense, you need to have a robust network in place. You need to have the basics of your control systems. You need to have panels with cabinets that have either, again, managed or unmanaged switches, but ultimately allow you to control the network. You also have, and this is going to be the last conversation piece, you have what's called the cloud, right? So your switch can then talk to the cloud, and this is where you can store some data on AWS, Azure, GCP, or a variety of other solutions. You can also start to program, right? So there's going to be different tools. And again, if we discuss this maybe in a separate video, we'll go into a little bit more detail, but you have remote connectivity from the internet back into your plant. And so contractors can now have access to specific maybe areas or PLCs they're working on. So ultimately, all of this relies on the piping or the industrial networking component that needs to be right in order for the facility to have this level of automation. So remember that each cell has its own automation process, and then this cell has its own automation process. But these two cells are interconnected. Similarly, these two cells are interconnected, and perhaps you don't necessarily need to interconnect the different lines. Maybe they're replicas of each other, but ultimately they're also being brought into the same MES and SCADA system in order to understand which line is doing better, on which line we're running maybe a different SKU. What are the opportunities for us to improve between different shifts? So this is, I want to say, the highest level of automation that I have seen. And of course, there's a lot more details to all of this. You have a lot on the IT side that we haven't necessarily discussed, but I wanted to keep it a little bit OT focused. If you have any questions, once again, about the topics that we talked about, or about the different layers of automation, about how to progress your career in automation, or maybe make some changes in your facility on the various sides. If you're talking to different leaders in automation, don't hesitate to leave me a question below, and we'll see you next time.
Yeah.